Okay, we start the second part of the class with an example. This example is for application of the results for turbulent boundary layer on a flat plate. So, we have the following situation. We want to estimate the force and power required for a supertanker, a very, very large flat ship that carries cargo, or I guess oil, to overcome friction drag at a cruising speed of 13 knots in seawater. And the dimensions are given there as 360 meters long, 70 meters beam, and 25 meters draft. I'll explain what these are because this is nautical terminology. I didn't even know what it was. I had to look it up. So let's. This term draft means basically the vertical distance between the waterline to the bottom of the hull. This one is just the width, basically, of, well, it says beam width. So if we do a picture of how this would look like, it would be, this is supposed to be a very long ship. And we just make it rectangular, supertanker, let's see, and we have the water level somewhere so this is water and this distance here between the waterline and the bottom of the hull of the tanker is the 25 meters. This is the distance between. You had your sandwich way too fast, I think. Oh, that's funny. 360 meters, and then we have this distance here, 70. Does the picture make sense to you? Yes? And the ship speed is 13 knots. A knot is a nautical mile per hour, so we're going to have to do the conversions to meters per second. So U is equal to 13 nautical mile per hour. We'll use our grid method here to be able to convert properly. Each mile is 6,076 feet per nautical mile. And then we are going to go to meters, so 0.305 meters per feet. And then we want to go to seconds, so 1 over 3,600 hours over seconds. Yep. And we put that in the calculator, and I've done this yesterday, got 6.69 meters per second. We got the speed. What else are we going to need? The properties of the fluid. So we look up the properties of seawater. We're told that this is seawater at 10 degrees Celsius, so we look that up. Degrees Celsius, and we get nu from a table somewhere 1.37 times 10 to the minus 6 meters squared per second. And so now we can get the Reynolds number. Well, the density is included in here because I'm going to use the Reynolds number with nu rather than just to save a little bit of work. So Reynolds is going to be U times L over nu. We have everything. 6.69 meters per second. The length is 360 meters. And then we have nu, which is 1.37 times 10 to the minus 6 meters squared per second. .76 times 10 to the 9. So for lack of a better thing to do, we're going to use the result for a boundary layer in a flat plate, and we're just going to say, okay, what are the flat plates that are subject to this drag? And we have, obviously, the bottom is a flat plate that is dragging against the seawater, but we also have the two sides. So, but obviously, there are other things that we are ignoring as well in this calculation. The drag would have other effects that we haven't discussed, which are due to waves. Breaking the surface, it has a wave drag that we haven't touched yet. So we're just looking at the force and power required to overcome the friction drag. If we wanted to add other effects, we would have to do that afterwards. We have the Reynolds number, so we're going to calculate now the coefficient of drag using the formula that we just presented for the mixed boundary layer. So it was 0.031 over the 7th root of the Reynolds number and minus 1,440 over Reynolds. Sorry? This is what we said just at the very end before the break, which was if you have a mixed boundary layer, you have to adjust for the fact that in the very front of the flat plate there will be a laminar region. And it's all empirical, so there's no an analytical result here that we've used. It's been obtained from many experiments. Question? Well, it's going to make a very little difference, in fact, because if you see this is 1.76 times 10 to the 9. If I put it in here, this is going to be a tiny number. But it's mostly going to be the turbulent part that contributes. But you could, I mean, there is a part of the boundary layer that is the boundary layer always starts from x equals 0, right? And we used x in our Reynolds number. It was Reynolds number with respect to x. And so this beginning part there will be a small area of laminar and then turbulent, always.
So is this a more general equation than the other two?
You would use this equation, this full equation, and if you calculate it and this turns out to be almost 0, it doesn't it won't make much of a difference. But you need to see first. You need to put it in the equation and see first if it contributes or not, because every flat plate will have a laminar portion in the front and then a turbulent portion. Yes? This Reynolds number that we've obtained is the Reynolds number with respect to the total length of the ship. If we were looking at the Reynolds number with respect to x, which is this case, that Reynolds number would go from 0 to this value at the very end of the plate. Yes, those are the available experimental results.
Yeah, so but we still use.
We don't have many other, we don't have results to 10 to the 9, but we just use the same equation. It's all empirical. This result is just going to give you an order of magnitude. This is engineering. It's not pure mathematics. And so you have to have the flexibility to approach the problem and solve it with the tools that you have at hand. This is the tool that we have.
Yeah, it's not really.
Yeah. There is no, those are the experimental, I mean, I haven't, researched the most recent literature on drag experiments. There might be a lot more. This is kind of the thing that you find in textbooks this is as much as you find in textbooks for the drag on a flat plate. Yeah, this is the tool we have available. No, it can't be negative. That would imply a problem somewhere. So we have the coefficient of drag. Now we can calculate the drag force due to just the flat plate friction. So remember, we're ignoring wave drag, we're ignoring other things, we're just looking at the flat plate friction. Okay, and for that we have D equals to coefficient of drag is there, 0.00148. Then the area, what is the area? We have 360 meters times this, let's see, where the bottom flat plate, right, 70. But we're also going to consider these two little stripes on two sides, which is 25 and 25. So 2 times 25, 50. That's the total area that is parallel to the flow of the ship. The bottom and the two sides. Then we have 1/2 rho of seawater, 10-20 kilograms per cubic meter, and V squared, 6.69 meters per second squared. And we can calculate that, and I get 1.46 meganewton. Pretty big number. Well, I'm using C of drag is equal to drag divided by 1/2 rho U squared A, and I've taken everything to the other side. All right, we have the drag, but we are asked to find the force, that's the force, and power. So to get the power would have to be this force times the velocity. So the power, I'm going to change colors here because I'm just going to use the little bits of white space that I've left. Power is going to be equals to drag times the velocity, and that is 1.46 meganewton times 6.69 meters per second, and I get, this is what I got, 9.7 megawatt. So this is a pretty big number. You agree? It's a pretty big number. So the power required is very large, despite the fact that the viscosity of the water is quite small. The reason is we have a huge area, and so even if the friction stress is small, when it acts over a large area, we get a lot of drag. And this is the situation for this supertanker. And we need almost 10 megawatt just to overcome the friction on the tangential surfaces against the water. And this is without counting the wind on the top and the wave drag and so on. So it's pretty... Okay? Question back there. Yes? We're looking at the friction drag only, not the pressure drag or wave drag or other forms. And the only surfaces that are tangential to the flow in this model are the bottom surface of a flat tanker and the two side areas. Those are the only areas that are tangential to the flow of the water. Why 25? Because there's one side here and there's one on the other side, so it's 25 times 2. Yeah, so two sides, one on, the two stripes on each side of the ship, 25 times 2. This equation? Yes, this equation, well, it's adopted by engineers through extensive experiments. I mean, people in the 50s and 60s published like 500-page books on measurements, experimental results of drag. And there's really zillions of man-hours that went on experiments with different shapes, surfaces, roughness, and so on. For the flat plate, then all of these were put on a curve, and this is the closest empirical result that has been adopted for that case. Flat plate, just for the flat plate, friction drag only. So flat plate completely parallel to the flow. Okay? Right, so now we are going to discuss pressure drag. So we consider a flat plate now, but normal to the flow. What we're going to experience for a flat plate normal to the flow is separation. The flow is not able to go around the back of the flat plate, so there's going to be separation at the edges here, and a wake. This is the wake in the back, a low pressure region called the wake. Notice that for the case of the flat plate, we have that the wall shear stress is perpendicular to the velocity, the free stream velocity, and so in our integral expressions that we wrote, where we had this angle theta, this angle is now 0 degrees, and so basically tau sine theta is 0, and we have that friction does not contribute to the drag force. We have only pressure drag. So D is actually just, let's use a little p here to indicate that the pressure drag only, integral of PdA, cosine of the angle is 1, and the flow separates, as I said, from the edges of the plate, and there is reverse flow in the back. And for this case, again, we have no analytical results. We only have experimental results in which the coefficient of drag CD is expressed as a function of the aspect ratio. L over D or L over B, and I have a little table here, and this is the type of thing that you find in the books or manuals, notice that the Reynolds dependence disappears above a certain, so this table says 10 to the 4, but some of the original sources say that above Reynolds about 1,000, This guy is being a little bit more conservative and he's saying 10,000. So 10 to the 3 really then. The drag coefficient is practically constant with respect to Reynolds number. The reason being that once, this separates at the point, at this point, we have if this is supposed to be rather like a sharp plate, then it always separates at a specific point. And we have backflow there. And it's all pressure drag, so the effect of Reynolds number is minimal. It's just the effect of the separation produces all the drag. Separation of the flow is what causes all of the drag. I think I have a couple of movies next to show you. Small little videos of experiments. And then we'll make a little summary, and then I'm going to discuss a little bit more flow around a sphere, flow around a cylinder. As much as we can today. Okay. Oop, go back. There we are. So here we have some videos. In the top you have a flat plate, which is laminar in the sense that the flow is quite slow-ish, but you always have this area of recirculation regardless. If the flow is quite fast, you have this turbulent area in the back. And you can see basically that beyond a certain Reynolds number, it's always going to be turbulent behind the flat plate. A horizontal plate will have a very, very small wake, and if the thickness was 0, the pressure drag would be 0. But there's always, in real life, some finite small thickness. But most of the drag will be friction drag. In this case, we have another blunt object, a cylinder, and you can see again the separation for that case. So let's do a quick summary of some main ideas that we've introduced. One is that the friction drag is 0 for a flat plate normal to the surface. Normal to, what did I say? No, I meant to say the flow. Normal to the flow. Normal to the flow. And it's going to be a maximum. The friction drag is going to be a maximum for a plate parallel to the flow. Since in this case the friction drag equals the total shear on the surface, in the case of the flat plate parallel to the flow. Now, drag for this flat plate normal to the flow is entirely pressure drag then. In the case of an object such as the cylinder, for another type of bluff body like a cylinder, then drag is a combination of the two. Friction drag is a strong function of viscosity because Reynolds is inversely proportional to the viscosity. Reynolds goes as 1 over the viscosity, and friction, of course, friction drag is a strong function of viscosity. It's due to friction, and so the contribution of friction drag to total drag is less and less as you increase the Reynolds number.
Reynolds is proportional to?
Yes, it varies as 1 over Reynolds, 1 over viscosity. And in the case of bluff bodies for large Reynolds numbers, the friction drag can mostly be neglected because it's going to be mostly pressure drag. If the Reynolds number is large, the viscosity is very small, and so friction drag contributes little. It's mostly pressure drag. But at low Reynolds number, then most drag is due to friction drag. So, for example, flow at very small scales. And so when Reynolds numbers is, say, less than 1, then most of the drag is due to friction. And the pressure drag is most significant when the flow separates. Separation is a very important problem and causes a lot of drag, and so that leads on to the idea that if you want to reduce drag, what would be a way to reduce drag? Change the shape so that there's less separation. This is the process of streamlining. Reducing the drag by streamlining is basically the idea of changing the shape of the object such that you reduce separation. And but notice that streamlining will have opposite effects on pressure drag and friction drag, because to produce a streamlined object, you may be forced to increase the area for a given cross-sectional area. A cylinder might look like that, and a airfoil will look like that for the same cross-sectional area. And so even though here we have less pressure drag, we have increased the friction drag because we've increased the area tangential to the flow. And so the concept of streamlining, so it requires one to look for an optimum situation, and in this case, this is the relationship between the cross-sectional, the diameter, if you will, if it was a cylinder, this cross-sectional distance here, and if you think about this as a projected area, it will be per unit length in the direction perpendicular to the paper, to the projector, right? And so we're looking at just the cross-section. And as you make the object more streamlined, L has to increase. And you have this competition between friction drag and pressure drag, and the total drag will be the sum of the two. But there is an optimum found where the total drag is a minimum. Does that make sense? And so let's discuss a little bit the flow around a sphere. Okay, so I had this example again of this. Before I do that, the sphere. This example is to emphasize the idea of streamlining. We have here a plot of an elliptical cylinder. So this is, we're looking again at a cross section. So this would be a cylinder like that, but we're looking at the cross section. And depending on the aspect ratio, these are the values of the lift coefficient. And you can see that for L over D equal 1, the lift coefficient, so this is a circular cylinder, the drag coefficient is about 1. So for a circular cylinder, CD is about 1. But as L over D goes to 0, then the cylinder becomes a flat plate. For a flat plate, CD is about 1.9. And also you notice that above more or less an aspect at L over D of about 4, then the CD becomes nearly constant. Being a good choice for minimum drag, L over D equals 4. Okay, so now let's discuss the flow around a sphere. For the flow around a sphere, we have the following options. For Reynolds number very low, Reynolds number very low is the case of Stokes flow that we have already discussed before. We can actually get an analytical result, and that analytical result is for Stokes flow. We got, this was I think lecture 17 or so, a result that the coefficient of drag was 24 over Reynolds. That's for Stokes flow. If you increase the flow, then you will have the drag coefficient, which is going, so notice that the drag coefficient here is decreasing with increase in Reynolds number. And the drag coefficient normally continues to decrease with increase in Reynolds number, but because of separation, it decreases more slowly than in the case of Stokes flow. And there's a very interesting thing that happens, which is that, the turbulent wake develops, as you can see here, right? A turbulent wake develops in the back. But so this is cause of large pressure drag, of course, but there is a point when the boundary layer in the front of the cylinder becomes turbulent. When the boundary layer in the front, this is a sphere, sorry, in the front of the sphere becomes turbulent, because there is an increased momentum flux. Remember, the boundary layer when it becomes turbulent is thinner. So there's an increased momentum flux. Because of that increased momentum flux, imagine the particle of fluid going around the sphere, it has more of an inertia and it's able to go around a little bit more, and it produces the effect of the separation point moving. So this is the laminar boundary layer and this is the separation point. Okay, separation point there and there. Then this is laminar. For the turbulent case, the separation point moves backwards a little bit. I'm going to do it in the same point. This is turbulent. It's going to move backwards, something towards the rear, because the particle fluid has a little bit more inertia, if you will, to go around the curved surface. And so this has the effect of making the wake a little bit more compact, the pressure difference between the rear of the sphere and the front being less and the drag being less. That happens when the boundary layer becomes turbulent. And that is, of course, the effect that is used in sports. And here's a plot. I'll show you in a moment. That's the effect that we're talking about. This is a plot of the coefficient of drag. This area over here would be the Stokes flow area, where the coefficient of drag is 24 over Reynolds number. From this section over here, the Reynolds number continues to decrease. The CD continues to decrease, but more slowly than the case of Stokes. And we have separation behind the sphere. In this case over here, look at this. There's a very important thing that happens there, which is there's a sudden reduction of the drag coefficient due to the fact that the boundary layer in the front of the sphere becomes turbulent. The momentum flux is higher. The particles are able to go around the sphere a little further to the back, and this delays separation. So the separation point moves a little further to the back, and you get a more compact wake, and this reduces considerably the drag. This is sometimes called the drag crisis. It suddenly drops, and this is the spot where you want to perhaps work your sports balls, right? This is the effect of if I show you the case of the golf ball, this is what you want to have. The laminar boundary layer, this is laminar, is a little bit thicker. Turbulent boundary layer, there's transition somewhere. Turbulent boundary layer becomes more, the fluid particles become more able to travel a little further around the curvature of the ball, and separation is delayed, and so the wake is thinner. This is why the golf balls have dimples, to trip the boundary layer into becoming turbulent, so that you will obtain that advantage from the turbulent boundary layer.
Does the spin change it too?
The spin produces something different, and we will discuss that in the chapter related to lift. But what we're looking at here is the effect of tripping the boundary layer to become turbulent, thus allow the particles of fluid to cover a little bit more of the curvature in the back, reducing the width of the wake.
Why is this?
Okay, what we're talking about here is the effects of the boundary layer. Remember that the boundary layer, when we discussed the boundary layer of a flat plate, we said when the boundary layer becomes turbulent, it is much easy for the fluid particles to transfer momentum to each other. When the boundary layer becomes turbulent, there is a superposition of many eddies in the flow of different sizes, and it's easier for the fluid particles to exchange momentum. There is more momentum flux. Yes?
So is this specific to this year, or does this work for
This is specific to the sphere. The cylinder experiences something similar, but not quite as much. But this is it's very dramatic for the case of the sphere.
So like
an airfoil is not a bluff body, and you don't have the wake. If you did, it wouldn't generate lift. And so it doesn't experience this effect at all.
So where does the
For example, if we go back to this point, it happens at a certain Reynolds number of about around, what is it, 2 10 times 10 to the 5 for the sphere. if you look at this, there's a point of separation here, the boundary layer. Then instead of the separation, what you have is some sort of transition here at the front. There's always boundary layers, transitions from laminar to turbulent. When it becomes turbulent, it is much more, it's just the increase of momentum flux that the turbulent boundary layer has, allows it to go around the curved path easier so that it delays the point of separation further down the back.